I'm going to talk about the use of Scheme for scientific computing from a perspective of an impatient schemer who wants to use currently available Scheme implementations, dialects, and related tools. And that's from a background in physics research and overlapping fields like machine learning. Scheme and Lisp languages in general have never been a widely adopted choice for physics, but there are very interesting examples. For instance, there are these seminal works from the early 90s based on the supercomputer toolkit that was a framework to build special purpose machines, like the machine that was used to integrate the motion of the solar system, leading to important scientific results, probing the chaotic nature of this motion. The toolkit featured a low-level assembly language and a high-level language. Both of them were Scheme. And I think this example it is nice because it shows the flexibility of Scheme to perform both low-level tasks, like those of assembler, but also to represent high-level functional mathematic notation. Scientific computing nowadays relies on several libraries that have vast functionalities, and a common design it is the one that involves a low-level language like C, C++, or Fortran, which is used as legacy code, so old code that is being vastly optimized and tested. But often it is also a choice dictated by efficiency issues of a high-level languages like Python or R that are more expressive. Scheme, it is at the same time a simple language, very well suited to represent physics equations, for example, and it also provides efficient implementations. Just to have an example and consider the following Scheme systems. So this is by no way a comprehensive overview of the available Scheme system. There are other languages that are very efficient. I select this based not only on efficiency but also on community resources. And Chez Scheme and Gambit, there are Scheme implementation that rely on very efficient compilers, in the same ballpark as the Steelbank Common Lisp compiler, so typically just a few factors lower than C, which is a huge improvement over languages like Python, where native Python code can easily perform hundreds times lower than C. And then another nice implementation it is Chicken Scheme, although it is typically somewhat slower than Chez or Gambit, and Racket, which is a Scheme descendant. It is not, strictly speaking, a Scheme implementation. And among these four, it provides probably the most complete system. So, beside efficiency, also parallel computing, it is an important aspect for a language used for scientific computing. And Racket, for instance, it provides features and places for more parallelism, plus high-level extensions like parallel maps that are very handy. Chez Scheme also implements native threads for different architectures, but it lacks so far of a high-level parallel forms, so that's more difficult to use, And Gambit and Chicken, on the other hand, they only implement green threads, although Chicken, it does have an extension to function from the MPI message passing interface, which is a popular framework for distributed computing, and it also has a parallel map extension. And to build, to distribute, and to easily install libraries, package managers are also an important part of a language. So Chicken and Racket, they have their own package manager. Chez Scheme doesn't have one, but it is supported by the Akku, which is a cross-platform scheme package manager. There are also other, that's the one I'm most used to. Gambit, it doesn't have a package manager, but I should mention that Gerbil, which is a scheme built upon Gambit, it does provide a package manager. In terms of available libraries, apart from the cross-platform Snowspheres and the very useful SR files, Chicken repository, the X, it contains about 400 packages, of which 11 are tagged for mathematical purposes, and the Racket, it contains more than 1000 packages, of which about 20 are tagged as mathematic packages. As a comparison, the Python package index, it lists currently more than 10,000 packages labeled as scientific. So here we're talking about a difference of 3 orders of magnitudes, and the lack of basic scientific libraries implementing fundamental numerical algorithms. I think that's the main issue that the impatient schemer is going to face. And then there are also other development tools, for example, C for in-function interfaces, which are important given the lack of native libraries, debug and profiling tools, which are important to write efficient code, documentation tool, and also tools for interactivity, which is an intrinsic aspect of Scheme and Lisp development, and it is very common also in Python development, through the IPython or the Jupyter notebooks. So we have efficient systems and nice development tools. The question is whether one can apply them to concrete scientific computing problems. So here, just to have a concrete example in mind, as a first use case, I consider the following problem, which is given pictures of a hand sign, of the American hand sign alphabet. The task it is to attribute the correct letter to a given picture. So that's a typical computer vision classification problem, which is nowadays tackled with the convolutional neural networks, which are not very straightforward algorithms, especially if one consider that they have to be very speed and memory efficient. For instance, if one take the BGG16 architecture, which is an advanced convolutional neural network model, it depends on 10 to the 8 parameters, and the training step, it involves algebraic operations over all of these parameters in iterative procedures that involve 10 to the 5 iterations. So one need optimized libraries that are available. For instance, from Python there are NumPy for manipulating arrays, SciPy that implements basic scientific computing algorithms. So they usually wrap C, C++, and Fortran code, and Keras, which has a Python interface using other libraries as a backend, like a TensorFlow written in C++. And the nice aspect is that all this library, even though there are different projects, they provide a very uniform and consistent interfaces. So if someone knows how to use NumPy, then it is relatively easy and intuitive to learn how to use the interface of Keras. And another important aspect, it is the interactivity requirement. It is important to interact with the running process. For instance, to stop the training step if the given accuracy it is reached, or to tweak all the model, the parameters of the model if one realized that the initial one, they were not good enough. But given this picture, it can be quite overwhelming for an impatient schemer to face this kind of problem. The best way is probably to write wrappers around the existing Python or C++ interfaces, but then there is not clear advantage of using Scheme over using user-friendly existing implementation like Python implementations. Still, Scheme can be a competitive tool in this field. For instance, consider the interactivity requirement, or also to combine different architectures, which are programs, so to combine programs in a functional way. But that's most likely work for a patient and expert schemer, given the efficiency requirement. Fortunately, not all applications require that involved algorithms. And as a second use case, I'm going to consider this work developed in cosmology. So we were playing with the cosmology perturbation theory, and we had an expression that involved hundreds of integrals, and we wanted to deal with them programmatically. So this problem involved numeric and symbolic operations. As common, we had a C++ core for the speed requiring part, wrapped by a Python interface that provides users with the mathematical expressions matching the physics equation of the problem. As an example for the operation that were involved in those integrands that we wanted to process programmatically, there were, for instance, differential operator. So let's take this simple one, which is just the second derivative plus the first derivative that will be applied to a given function. So this operator can be applied once, or it can be composed with itself to be applied 2 times. And there are different ways to face this problem. So one can use a symbolic differentiation. That's what we did at the C++ level. But that's inefficient because it led to long expressions that take correspondingly long to evaluate. Another option it is to use finite differences, which however they typically led to large numerical errors, much larger than machine precision. Automatic differentiation would have been the most ideal solution, which provides a derivative at machine working precision, and it is much more efficient, the symbolic differentiation. So if we did use Scheme, we could have implemented this differential operator just importing the AD library for automatic differentiation, which is an R6/RS compliant library. And the differential operator would have been applied to some procedure, and the definition returns itself a function, because the derivative of a function, it is still a function that will be eventually evaluated at some value of x, and we define it as the sum of the derivative applied 2 times to the procedure plus the derivative applied 1 time. And then having this operator, one can apply it 1 time to a function at a given value of x, let's say 1, and one can compose it with itself to apply it twice to a given function. So that's easy, almost trivial, but that's because that's Scheme. If that was a C++, that the interface, the code would have been more involved. It would have the required change to the code, at the very least, to use different types, implementing given external automatic differentiation libraries. Python, for instance, also provides very user-friendly libraries that are as expressive as Scheme, but That operation were dealt at the C++ level precisely because of Python efficiency issues. So using a unified scheme libraries instead of a C++ and Python would have allowed us to use an efficient implementation like Scheme and still very expressive, mirroring very precisely the functional mathematical notation that we were using. This project did not rely on several external libraries, and so using Scheme would have just removed cumbersome layers of software engineering. And contrary to the first use case, this example was within the reach of an impatient schemer, not even necessarily expert one. So my conclusion are that Scheme, it is well suited for numerical and symbolic computations. It is a very interesting perspective to replace cumbersome practices that involve, for example, C++ core plus Python interfaces that come with their own limitations. And from a perspective of an impatient schemer, projects building upon simple components, they can already be tackled with existing scheme systems. However, more in general, there's still a need of more libraries for basic numerical algorithms. So library analogous to NumPy or SciPy in Python. And this could serve as a common ground to then develop more specialized applications.
Okay, we have plenty of time for questions. Well, I have a question if no one else does. Maybe I missed it. Did you do any benchmarks to compare the performance of this against your previous system?
Yeah, so I did benchmarks for Scheme implementations and Racket. For benchmarks comparing schemes and Racket to C, I relied on some literature and other benchmarks that are available on the web. So regarding scheme systems, so the benchmarks that I did, I took the Larceny benchmarks, which are R7 RS portable code. So the general picture is that for the 3-scheme system plus Racket that I mentioned is that the Chez Scheme and Gambit, they're often the fastest implementation. And Racket is usually on the ballpark of 1, 2, 3 times slower. And instead the chicken scheme is more toward 4 or 5 times slower than Chez on Gambit. So these benchmarks were just supposed to give an idea of the ballpark to place these languages. Then, of course, as all benchmarks, there are a lot of subtleties that comes in. For example, the optimization flags of a given compiler, and so on, and especially the programming style of a given program. And so the variance between different programs can be larger than the variance between different languages if they are in the same ballpark.
Very nice. Any other questions? You can either type them in the chat or raise your hand in Zoom. It looks like we have a question.
Yeah.
We have a few questions I missed. Go ahead.
Okay, I see a question. Okay, so there are other that I missed. Do you have any feedback on particular exercise for mathematics? For instance, exercise 179, non-empty intervals and generalized arrays, and exercise 164, enhanced multidimensional arrays. So I didn't use those particular benchmarks. So one reason is that one language that I'm using, it is Racket, which has a very nice mathematical built-in library that also includes operation on arrays. And it also has a wrapper to BLAS, and also other implementation like a chicken scheme, they have wrappers over BLAS. BLAS, it is a very common numerical library, efficient, very well optimized. So that's what I use as first glance. But now I will certainly have a look also at this SR5s, but I didn't test them. I don't have any benchmarks on that. For the SR5, something that I like, for instance, is the 42 for this comprehension, at least coming from Python. I like it in Python, this comprehension are widely used, not only for style, but also for performance issues. And the SR5 42 also perform general comprehension, and the scope it is much vaster than Python comprehension. It is, and the use it is not necessarily dictated by performance issues.
Okay, we have a question from Jason Heeman. Do you want to ask that?
Sure.
Yeah.
Oh, you can see it down there just as well as I can say it.
Why don't you go ahead and say it, Jason?
I asked in the chat if we have some notion of how many of those multiplicity of Python libraries are also essentially just wrappers over old existing legacy code. I thought what came to mind was the linear algebra package being old Fortran that gets wrapped up in just about everything.
Yeah, I think this design of the low-level language used for efficiency issues plus the Python wrapper, it's very common. Basically, all the fundamental routines in projects like NumPy and SciPy, which are the basic used by everyone, they all relies on the C, C++, Fortran, and it is also common to use other Python-like languages like Python. For performance issues, so a lot of them are wrappers to other libraries written in low-level language. And also, I was comparing the number of languages of available libraries. That's of course not the optimal comparison measure. One also should look at how much functionalities a library has. And so on. For instance, the math library for Racket that I mentioned before, it already has a lot of very useful tools. And it is actively developed, so I think it is a very nice project.
Thank you.
Okay, Raul, do you want to ask your question?
Yeah, sure. Actually, with the Julia language, we saw the apparition of some new wrapper techniques. I wanted to know if you had a look at that in Scheme, because there is at least a dark art library that exists for that. Did you have a try?
Yes, I gave a try to dark art. So dark art it aims to support directly the binary interface of high-level languages like Python, Julia. So it is another way to bypass the problem of the lack of libraries. Instead of writing by hand the wrappers, one has just directly access to Julia and Python. I think it is a very interesting project. Of course, using directly native libraries, it has its own advantage. If I'm going to use a native library for Scheme that implement arrays, let's say, I can go to look at the source code and modify it if I need it. But if I'm going to use a wrapper to BLAS or LAPACK, I probably don't even try to look at the source code of BLAS and LAPACK to modify it. And Python wrappers similar to what's done in Julia. So there are automatic fairly automatic wrappers like Swig. which are a quite impressive project, and I use it to build automatically wrapper C++ code. For the particular case of Python, it has its own limitation related to the parallel computing part that I was mentioning. For example, to bypass the Python global interpreter lock, it is necessary to deal with objects that can be serialized in a given way. For instance, internal function cannot be serialized and parallelized with the Python standard libraries. And something that I find often is that wrapper generated that way cannot be used to parallelize at the Python level. And I think that parallel computing should be an integrated aspect of a language meant for scientific computing.
Okay, let's see. We did have one person's hand up. That went back down, so I'll move to Charisse. Do you want to ask your question?
Hi, great talk. Also, thanks for saying my name correctly, Charisse. I was wondering, you mentioned finite differences, and I was wondering what the experience you have using different PDE solving techniques, and why, if you've tried FEM and finite volume method and things like that. And I apologize if you mentioned this already in the talk.
No, I didn't mention that. So differential equation, I don't have much experience from the scheme side. And that's usually because they belong to a part that it is efficiently requiring. If I were to use scheme, I think rather than finite differences that led to large errors, I'll use automatic differentiation libraries. For instance, Julia now, that was mentioned in the question before, it also has a very nice library to solve a differential equation just using automatic differentiation, which is a very widely adopted algorithm, also in view of machine learning uses. But for specific solving differential equation with scheme and using finite element differences, I don't have much experience with that.
Thank you.
Thank you.